The statement that a portion of the conductor that is the sole connection to the grounding electrode conductor shall not be required to be larger than 6 American wire gauge copper or 4 American wire gauge aluminum wire is not entirely correct. Section 250.66 specifies that the portion of the grounding electrode conductor, abbreviated GEC, that serves as the sole connection to the grounding electrode or electrodes is not required to be larger than 6 American wire gauge copper or 4 American wire gauge aluminum wire. This implies that if the grounding electrode conductor is connected only to the grounding electrode, such as ground rods, it does not necessarily need to be sized according to Table 250.66. However, the grounding electrode conductor must still be sized in accordance with Table 250.66 if it is connected to any other equipment or devices, for example, the service entrance equipment. In a scenario involving a 400 amp residential service with no other grounding means other than ground rods, the grounding electrode conductor would still need to be sized according to Table 250.66. Let's delve deeper into grounding electrode conductor sizing based on the National Electrical Code, or NEC. The grounding electrode conductor, abbreviated GEC, connects the service equipment to the grounding electrode system. Its purpose is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. Now, concerning the size of the grounding electrode conductor, the NEC provides specific guidelines to ensure effective grounding. Table 250.66 is commonly used to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. However, Section 250.66 introduces an exception for the portion of the grounding electrode conductor that is the sole connection to a grounding electrode or electrodes. In simpler terms, if a section of the grounding electrode conductor only connects to grounding electrodes like ground rods and nothing else, it does not need to be sized larger than 6 American wire gauge copper or 4 American wire gauge aluminum. It is important to understand the implications of this exception. Firstly, if the grounding electrode conductor connects to the service equipment and then extends to the grounding electrode, the entire conductor must be sized according to Table 250.66, corresponding to the size of the service entrance conductors. Secondly, the exception only applies to the portion of the grounding electrode conductor that is exclusively connected to the grounding electrode. If the grounding electrode conductor is connected to any other equipment, such as a metal water pipe, the exception does not apply, and the entire conductor must be sized according to Table 250.66. Thirdly, in situations where multiple grounding electrodes are used, such as a combination of ground rods and a metal water pipe, the grounding electrode conductor must be sized according to the largest grounding electrode required by Table 250.66. Now, to address the specific scenario of a 400 amp residential service with ground rods as the sole means of grounding, the grounding electrode conductor must still be sized according to Table 250.66. This is because the grounding electrode conductor connects to the service equipment before extending to the ground rods. The exception in Section 250.66 does not apply since the grounding electrode conductor is not solely connected to the grounding electrodes. To determine the appropriate size of the grounding electrode conductor for a 400 amp service, refer to Table 250.66. The table correlates the size of the service entrance conductors or equivalent area for parallel conductors to the minimum size of the grounding electrode conductor. For example, if the service entrance conductors are 500 kc mil copper, Table 250.66 specifies a minimum grounding electrode conductor size of 1/0 American wire gauge copper. It is important to note that this is just an example, and the actual size of the grounding electrode conductor must be determined based on the specific size of the service entrance conductors used in the 400 amp residential service. Now, let's consider some additional factors that may influence the size of the grounding electrode conductor. Firstly, if the grounding electrode conductor is made of aluminum, it must be protected from physical damage if installed where exposed. Secondly, the grounding electrode conductor must be continuous, or spliced by reversible compression connectors listed for the purpose, or by the exothermic welding process. Thirdly, the grounding electrode conductor must be securely fastened to the surface on which it is carried. It is crucial to consult the latest edition of the National Electrical Code and local amendments for the most accurate and up-to-date requirements regarding grounding electrode conductor sizing. Improperly sized grounding electrode conductors can compromise the effectiveness of the grounding system, potentially leading to electrical hazard. The grounding electrode conductor plays a vital role in ensuring electrical safety by providing a low impedance path for fault current. Correct sizing of the grounding electrode conductor is essential for effective grounding. It is not acceptable to assume that the exception in section 250.66 applies to all grounding electrode conductors connected to ground rods. The exception only applies to the portion of the grounding electrode conductor that is exclusively connected to the grounding electrode. For services, the grounding electrode conductor must be sized according to table 250.66, based on the size of the service entrance conductors. Let's further explore the nuances of grounding electrode conductor sizing by examining a few additional scenarios. Suppose we have a 200 amp residential service with a water pipe electrode and supplemental ground rods. The grounding electrode conductor is connected to the water pipe and then extended to the ground rods. In this case, the entire grounding electrode conductor must be sized according to table 250.66, based on the size of the service entrance conductors. The exception in section 250.66 does not apply because the grounding electrode conductor is connected to the water pipe electrode. Alternatively, imagine a detached garage with a sub-panel fed from the main service panel in the house. The detached garage has its own grounding electrode system consisting of ground rods. In this scenario, the grounding electrode conductor for the detached garage sub-panel only needs to be sized according to section 250.66a. This is because the grounding electrode conductor is solely connected to the ground rods and not to any other equipment. Therefore, it does not need to be larger than 6 American wire gauge copper or 4 American wire gauge aluminum. Now, let's consider the scenario of a large commercial building with multiple service disconnects. Each service disconnect has its own grounding electrode conductor connected to a common grounding electrode system. In this situation, each grounding electrode conductor must be sized according to table 250.66 based on the size of the corresponding service entrance conductors. The exception in section 250.66 does not apply because the grounding electrode conductors are connected to the service equipment. It is important to recognize that the grounding electrode conductor is part of a larger grounding electrode system, which includes the grounding electrodes and any bonding jumpers. The entire system must be designed and installed to provide a low impedance path for fault current to ensure the proper operation of overcurrent protective devices and minimize the risk of electrical shock. Now, let's discuss some practical considerations for installing grounding electrode conductors. Firstly, the grounding electrode conductor must be protected from physical damage, especially in areas where it is exposed. This can be achieved by using conduit, raceway, or other suitable protective measures. Secondly, the grounding electrode conductor must be securely fastened to the surface on which it is carried to prevent it from becoming loose or damaged. Thirdly, the grounding electrode conductor must be continuous, without any splices or joints, unless the splices or joints are made by reversible compression connectors listed for the purpose, or by the exothermic welding process. It is also important to ensure that the grounding electrode conductor is accessible for inspection and maintenance. This may involve providing access panels or other means of accessing the conductor without having to disassemble equipment or structures. Now, let's delve deeper into the specific requirements for grounding electrodes, as these are closely related to the grounding electrode conductor. The NEC specifies various types of grounding electrodes, including metal water pipes, metal frame of the building or structure, concrete encased electrodes, ground rings, and ground rods. Each type of grounding electrode has its own specific installation requirements. For example, metal water pipes used as grounding electrodes must have at least 10 feet of the pipe in direct contact with the earth. Ground rods must be at least 8 feet long and driven into the earth to a depth of at least 8 feet. Concrete encased electrodes must consist of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. It is important to note that the type and number of grounding electrodes required depend on the specific conditions at the site. The NEC provides guidance on how to determine the appropriate grounding electrode system for different applications. Now let's consider the scenario where the grounding electrode conductor is connected to a metal water pipe electrode. In this case, the grounding electrode conductor must be connected to the water pipe within 5 feet of the point where the water pipe enters the building. This requirement is intended to minimize the impedance of the grounding path and ensure effective grounding. Additionally, a bonding jumper must be installed around any insulated joints or sections of the water pipe to maintain continuity of the grounding path. Now, let's discuss the use of ground rods as grounding electrodes. Ground rods are commonly used in residential and commercial applications, especially where other types of grounding electrodes are not available or practical. When using ground rods, it is important to drive them deep enough into the earth to ensure good contact with the soil. The NEC requires that ground rods be driven to a depth of at least 8 feet. In some cases, it may be necessary to use multiple ground rods to achieve the required grounding resistance. The NEC specifies the spacing requirements for multiple ground rods. It is also important to ensure that the ground rods are made of a suitable material such as copper or galvanized steel to resist corrosion. Now let's consider the use of concrete encased electrodes as grounding electrodes. Concrete encased electrodes, also known as UFA grounds, are often used in new construction. They consist of a bare copper conductor encased in concrete that is in direct contact with the earth. Concrete encased electrodes provide a very effective grounding path due to the large surface area of the conductor in contact with the earth. However, they are typically only practical to install during the construction phase. Now let's discuss the importance of bonding in the grounding system. Bonding involves connecting together all metal parts that are likely to become energized during a fault. This includes metal water pipes, metal gas pipes, metal conduits, and metal equipment enclosures. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. Bonding jumpers are used to connect these metal parts together. The size of the bonding jumpers is determined by Table 250.102 cone in the NEC. Now let's consider the scenario where a metal water pipe is used as a grounding electrode, and there is a plastic section of pipe in the water line. In this case, a bonding jumper must be installed around the plastic section of pipe to maintain continuity of the grounding path. The bonding jumper must be sized according to Table 250.102 cone in the NEC. It is also important to ensure that the bonding jumper is securely fastened to the metal water pipe on both sides of the plastic section. Now let's discuss the use of surge protective devices, or SPDs, in conjunction with the grounding system. Surge protective devices are used to protect electrical equipment from voltage surges caused by lightning or other transient events. SPD are typically installed at the service entrance and at branch panels. To be effective, SPD must be properly grounded. The grounding electrode conductor for the SPD must be sized according to the manufacturer's instructions and the NEC. It is also important to ensure that the SPD is installed in a location where it is accessible for inspection and maintenance. Now let's consider the scenario where a generator is connected to the electrical system. When a generator is connected, it is important to ensure that the generator is properly grounded. The grounding requirements for generators depend on whether the generator is separately derived or non-separately derived. A separately derived system is a system where the generator is not electrically connected to the normal power source. A non-separately derived system is a system where the generator is electrically connected to the normal power source. For separately derived systems, a grounding electrode conductor must be installed from the generator to a grounding electrode. The grounding electrode conductor must be sized according to Table 250.66 in the NEC. For non-separately derived systems, the grounding requirements are different. Consult the NEC for specific requirements. Now, let's discuss the importance of regular inspection and maintenance of the grounding system. The grounding system should be inspected periodically to ensure that it is in good condition and functioning properly. This includes checking the grounding electrode conductor, grounding electrodes, and bonding jumpers for corrosion, damage, or loose connections. Any problems that are found should be corrected promptly. It is also important to ensure that the grounding electrodes are still in contact with the earth. Over time, the soil around the grounding electrodes may become compacted or eroded, which can reduce the effectiveness of the grounding system. In some cases, it may be necessary to add additional grounding electrodes or replace existing grounding electrodes to maintain the required grounding resistance. Now, let's consider the scenario where a swimming pool is installed. Swimming pools have specific grounding requirements to protect swimmers from electrical shock. All metal parts of the swimming pool, including the pool structure, metal conduit, and metal equipment, must be bonded together. A solid 8 American wire gauge bonding conductor must be used for this purpose. The bonding conductor must be connected to the equipment grounding conductor of the pool equipment. Additionally, a ground fault circuit interrupter, or GFCI, protection is required for all electrical circuits serving the swimming pool equipment. Now, let's discuss the grounding requirements for sensitive electronic equipment, such as computers and servers. Sensitive electronic equipment is more susceptible to damage from voltage surges and electrical noise. Therefore, it is important to provide a dedicated grounding system for this equipment. This may involve using a separate grounding electrode system or a specially designed grounding busbar. The grounding impedance for sensitive electronic equipment should be as low as possible to minimize the risk of damage. Now, let's consider the scenario where a building is located in an area with high lightning activity. In areas with high lightning activity, it is important to provide additional lightning protection. This may involve installing a lightning protection system, which consists of lightning rods, conductors, and grounding electrodes. The lightning protection system is designed to intercept lightning strikes and safely conduct the current to ground, protecting the building and its occupants from damage. It is crucial to consult with a qualified lightning protection contractor to design and install a lightning protection system that meets the specific needs of the building. Understanding the nuances of grounding electrode conductor sizing, along with the broader principles of grounding and bonding, is essential for ensuring electrical safety and compliance with the National Electrical Code. Always refer to the latest edition of the NEC and consult with qualified electrical professionals for specific applications and installations.